Every moment of your existence unfolds on a stage you cannot see. Every breath you take, every star that burns across the night sky, every quantum particle vibrating in the void, all of it exists within a single unified fabric. We call it spacetime, but what is it really? Is it a thing? Is it an illusion? Is it the scaffolding upon which all reality hangs? Or is it merely an emergent mirage born from something deeper, something that humanity has not yet discovered? For 3 centuries, space and time existed as separate concepts, fixed, immutable. They were the stage upon which the universe performed its eternal drama. Space was the container, time was the measure. Both were absolute, understood by Newton as the inert backdrop against which particles danced and forces acted. This worldview seemed unshakable, intuitive. It matched our lived experience, and it governed physics for 200 years. But in 1908, a German mathematician named Hermann Minkowski looked at Einstein's equations and saw something that changed everything. He perceived that space and time are not separate. They are woven together. They are one, he declared with radical conviction. Space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. 7 years later, Einstein revealed something far more astonishing. This unified fabric of space-time does not simply hold the universe inert. It bends, it curves, it responds to the presence of matter and energy, like the surface of a drum responding to a vibration. Gravity is not a mysterious force pulling objects across empty space. Gravity is the curvature of space-time itself. The stage beneath our feet is alive, dynamic, responsive, and perhaps most unsettling of all. Space-time may not be what we think it is. Recent discoveries suggest it may not be fundamental at all. It may be emergent, ephemeral, a hologram projected from dimensions we cannot see, a collective illusion woven from quantum entanglement at scales smaller than we can measure. This is the story of space-time. This is the story of how physicists discovered that reality is far stranger, far more profound, and far more fragile than any previous generation imagined. In the 19th century, the world was confident. Newton's laws reigned absolute. Space was absolute. A 3-dimensional void extending infinitely in all directions, unchanging, indifferent to the events occurring within it. Time was equally absolute, flowing uniformly everywhere at once, ticking forward at the same rate whether you were on Earth or in the remotest galaxy. Space and time were 2 separate rivers flowing in different directions. And physics was the art of understanding how matter moved through this fixed, inert stage. This worldview was so powerful, so intuitive that very few scientists questioned it. Mathematics seemed to confirm it, observations seemed to confirm it, and for the purposes of 19th century physics, calculating the orbits of planets, understanding the motion of projectiles, predicting the behavior of pendulums, Newton's framework worked with astonishing precision. But in 1905, a young theoretical physicist named Albert Einstein, working in relative obscurity at the Swiss Patent Office in Bern, published a paper that would quietly begin to shatter this worldview. He proposed something almost incomprehensible. The laws of physics are identical for all observers moving at constant velocity, and the speed of light is constant for all such observers. This second postulate seemed almost trivial, a mere technical assumption. Yet from it emerged consequences so bizarre, so counterintuitive, that even experienced physicists struggled to comprehend them. Time could dilate. A clock moving at high speed would tick more slowly than a stationary one. Length could contract. An object moving through space would appear shortened in the direction of motion. Most disturbing of all, simultaneity was not absolute. 2 events that appeared simultaneous to one observer would appear to occur at different times to another observer moving at a different velocity. The very notion of now became observer-dependent. These ideas were shocking. Many physicists dismissed them as mathematical curiosities, interesting puzzles but not reflections of physical reality. Yet the mathematics was impeccable, grounded in the constancy of light, which had been verified in laboratory experiments. Einstein's special theory of relativity was correct, but special relativity alone did not reconcile space and time. It merely showed that space and time were intertwined, that measurements of space and time depended upon the observer's motion. It was not until 1908 that Hermann Minkowski, Einstein's former mathematics professor at the Polytechnic in Zurich, perceived the true implications of Einstein's work. Minkowski made a simple but profound mathematical observation. The Lorentz transformations, the equations describing how measurements of space and time change between moving observers, could be reinterpreted not as relationships between different observers, measurements of a fixed stage, but as rotations in a four-dimensional mathematical space, combining space and time as a unified whole. He called this four-dimensional space Minkowski spacetime. In this conception, space and time are not separate dimensions that happen to be related. They are components of a single geometric entity. A point in spacetime is not just located at a position in three-dimensional space. It is also located at a moment in time. Every event in the universe, a supernova explosion, a human heartbeat, the emission of a photon, is a point, a location, in spacetime. The universe is not events occurring in space as time flows. The universe is the collection of all events, all points in spacetime, all of history simultaneously present in a four-dimensional whole. This perspective inverted our understanding of reality. Instead of thinking of a universe that evolves through time, changing from one state to the next, Minkowski's formulation suggested a universe that simply is, a four-dimensional block of space-time, with time as merely another dimension, fundamental and unchanging in its structure. Minkowski demonstrated this mathematically through the concept of the invariant interval. In ordinary three-dimensional space, the distance between 2 points is given by the Pythagorean theorem, d2 dx2 plus dy2 plus dz2. This distance is invariant. All observers agree on it. In space-time, Minkowski discovered an analogous invariant, s2 c2 dt2 plus dx2 plus dy2 plus dz2, where c is the speed of light. This space-time interval is the same for all observers, regardless of their motion. It is the true fundamental distance in the four-dimensional universe. The negative sign before the time component is crucial. It means that space and time, while unified, are not identical. Time is fundamentally different from space. This mathematical difference would later prove crucial to understanding gravity itself. Einstein himself was initially skeptical of Minkowski's geometric interpretation. Einstein preferred physical intuition to pure mathematics. He was reportedly dismissive, saying, "Since the mathematicians have invaded the theory of relativity, I do not understand it anymore." Yet within a few years, Einstein would realize that Minkowski's geometric framework was not merely an elegant reinterpretation of his special relativity. It was essential. It was the language in which nature itself seemed to speak. As the full implications sank in among the physics community, a profound realization emerged. Space and time are not what we thought they were. They are not separate, inert stages. They are unified, dynamic, geometric. This unified fabric, space-time, would become the foundation for Einstein's next great leap, a theory that would reveal gravity itself to be a manifestation of space-time's curvature, rewriting the foundations of physics and reshaping humanity's understanding of reality. In 1911, Einstein began to ponder a question that would consume the next 4 years of his life. How could he incorporate gravity into special relativity? The theory of special relativity described a universe where space and time were unified in a flat, four-dimensional Minkowski spacetime. Yet gravity, the force that held planets in orbit, that kept humans anchored to the Earth, had never been incorporated into this framework. Newton's theory of gravity still reigned, describing gravity as a force that acted instantaneously across space, pulling masses toward each other. But instantaneous action at a distance violated one of Einstein's core principles. Nothing could travel faster than light. In special relativity, the finite speed of light meant that information, influence, causality itself could not travel faster than light's limit. Yet Newton's gravity, as traditionally conceived, seemed to require exactly such instantaneous influence. If the sun vanished tomorrow, Newton's equations suggested that Earth would immediately cease to feel the sun's gravitational pull. But relativity forbade this. Something was deeply wrong. Einstein's solution came through a series of thought experiments, each more profound than the last. The most famous was his thought experiment of the falling elevator. Imagine an observer in a windowless chamber, suspended far from any massive objects. That observer floats weightless, experiencing no gravitational force. Now imagine the same observer in an identical chamber resting on Earth's surface. That observer feels pressed downward by gravity. But here is the crucial insight. These two situations are physically indistinguishable. The observer in the falling chamber experiences the same sensations, the same physics, as if no gravity existed at all. Conversely, an observer in an accelerating chamber far from Earth would feel exactly as if gravity were pulling them toward the floor. Einstein realized that acceleration and gravitational force are not merely similar, they are equivalent. Gravity and acceleration are the same thing experienced in different reference frames. This principle of equivalence was revolutionary. It suggested that gravity is not an external force acting on objects. It is a consequence of the structure of space-time itself. An observer falling toward Earth is not being pulled by a force. The observer is moving inertially, in a straight line through space-time. But space-time near Earth is not flat. It is curved over the following 4 years. Assisted by his mathematician friend Marcel Grossmann, Einstein developed a mathematical framework to describe how matter curves space-time and how this curvature determines the paths that objects follow. In 1915, he published the equations of general relativity. The left side describes space-time's geometry, its curvature and structure. The right side describes the distribution of matter and energy. The equations state a profound truth. Matter and energy tell space-time how to curve, and curved space-time tells matter and energy how to move. This was not merely a new law of gravity, it was a fundamental reimagining of what gravity is. Gravity is not a force in the Newtonian sense. It is the geometry of space-time. Objects move along geodesics, the shortest paths through curved space-time, and we perceive this motion as gravitational acceleration. The consequences of this insight were staggering. First, gravity should influence light itself. Light always travels at the same speed, even when moving through curved space-time. But if space-time is curved, then light should bend, following the geodesics of space-time's geometry. In 1919, during a solar eclipse, the British astronomer Arthur Eddington measured the positions of stars during the eclipse. If Einstein's predictions were correct, the sun's massive gravity should bend the light from distant stars, causing them to appear slightly shifted from their normal positions. Eddington's measurements confirmed Einstein's prediction, often to within the margin of experimental error. The second confirmation came from a phenomenon known for over a century: the precession of Mercury's orbit. Mercury's orbit is not a perfect ellipse. It slowly rotates, its perihelion, the point closest to the Sun, gradually advancing. Newtonian mechanics could account for most of this precession through the gravitational influence of other planets, but there remained a small, unexplained discrepancy. When Einstein applied his field equations to the gravitational field around the Sun, the predicted precession matched observations exactly. The 43 arcseconds of additional precession per century that had puzzled astronomers for generations was perfectly explained by general relativity. Yet, the full implications of Einstein's equations extended far beyond explaining the motion of planets. If space-time could curve, it could curve in extreme ways. It could curl around itself. It could be torn, twisted, oscillate. In certain regions where matter was compressed to extraordinary densities, space-time could curve so intensely that it would create a region from which not even light could escape. A black hole, though this term would not be coined until decades later. And if one traced the expansion of the universe backward in time, as the work of Hubble and Lemaitre would later suggest, the density of matter and energy would increase without bound. At some moment in the past, all of the universe's matter and energy would have been compressed into a single point, infinitely dense, where space-time's geometry would have been infinitely curved. General relativity predicted the existence of a singularity at the moment of the Big Bang. Einstein himself was troubled by these consequences. He added to his equations a term, the cosmological constant, represented by the Greek letter L, to balance the equations, to allow for the possibility of a static, non-expanding universe. This constant represented a mysterious form of energy pervading all of space, exerting a repulsive force that could counteract gravity's tendency to cause collapse. In 1931, Einstein renounced the cosmological constant as the greatest blunder of my life, accepting the overwhelming evidence that the universe was indeed expanding, not static. Yet the cosmological constant would return to haunt physics decades later, when observations of distant supernovae in 1998 revealed that the universe's expansion was not merely continuing, it was accelerating. Something was pushing the universe apart. Something was conquering gravity itself on cosmic scales. Einstein's greatest blunder would become perhaps the greatest mystery in modern physics. Dark energy, the nature of which remains unknown to this day. In the 1920s, the universe was believed to be static, eternal, unchanging. This was not merely a scientific assumption. It was almost a philosophical necessity. An eternal, static cosmos seemed more perfect, more complete, than one that had a beginning or one that might change. Even Einstein, despite his revolutionary equations, sought a static solution, adding his cosmological constant to prevent the universe from collapsing under its own gravity. Yet evidence was accumulating that challenged this ancient assumption. In the 1920s, Edwin Hubble, working with the newly completed 100-inch Mount Wilson telescope, began systematic observations of distant galaxies. These observations revolutionized astronomy and cosmology forever. Hubble noticed something extraordinary. The light from distant galaxies was shifted toward the red end of the spectrum. This redshift could be explained by the Doppler effect. When a light source moves away from an observer, the wavelengths of the light it emits appear stretched, shifted toward longer wavelengths in the red portion of the spectrum. Just as the siren of an ambulance appears to drop in pitch as it recedes, the color of light from a receding source appears to shift toward red. What was more astonishing was the relationship Hubble discovered. The redshift increased with distance. More distant galaxies showed larger redshifts, indicating they were moving away faster. Hubble quantified this relationship, discovering what would be called Hubble's law. The recession velocity of a galaxy is proportional to its distance. Expressed mathematically, v force h0, where v is recession velocity, d is distance, and h0 is a constant called the Hubble constant. The implications were staggering. The universe was not static. It was expanding. In fact, the universe itself, not merely galaxies moving through space, but space itself, was stretching and expanding. Every point in space was receding from every other point. It was as if the universe were a vast balloon being inflated, and the galaxies were dots on its surface, each moving away from the others as the balloon expanded. In 1927, just 2 years before Hubble's definitive observations, a Belgian physicist and Jesuit priest named Georges Lemaitre had already derived from Einstein's field equations that an expanding universe was not only possible, but predicted by general relativity. If the universe was expanding now, then in the past, it must have been smaller. If one traced this expansion backward in time, all the matter and energy of the universe would have been compressed into a smaller and smaller volume, at higher and higher densities and temperatures. Lemaitre proposed a daring idea. The universe had a beginning. It had originated in an extraordinarily hot, dense state that he called the primeval atom, a single point containing all the matter and energy of the universe. From this initial state, the universe had been expanding and cooling ever since. This idea of a cosmic origin seemed to contradict the steady-state universe of classical physics. Many scientists resisted it fiercely. Some saw in it an endorsement of religious creation myths, a confusion of physics with theology. Others found the concept of a singularity, a point of infinite density, to be physically suspect, perhaps a sign of the incompleteness of general relativity. Yet the evidence mounted. In 1929, Hubble published his definitive measurements, establishing beyond reasonable doubt that the universe was expanding. In 1948, George Gamow proposed that if the universe had originated in an extraordinarily hot state, it should have cooled over the past billions of years, yet traces of that primordial heat should remain, a thermal radiation bath filling all of space. This prediction seemed impossible to test. Then, in 1964, Arno Penzias and Robert Wilson, working with a radio antenna at Bell Labs, discovered something unexpected. No matter where they pointed their antenna in the sky, they detected a faint background of microwave radiation. This radiation filled the universe uniformly, coming from every direction. It was the echo of creation, the cosmic microwave background, the cooled remnant of the universe's primordial heat, predicted by Gamow decades earlier. The Big Bang Theory, as it came to be called, was now firmly established. Not only was the universe expanding, but it had originated in a hot, dense beginning. Time itself appeared to have had a starting point. The expansion of space-time had created the dimension of time. There was no time before the Big Bang. The concept was physically meaningless. In 1970, Stephen Hawking and Roger Penrose proved mathematically that general relativity predicted the existence of space-time. Singularities, points where density and curvature became infinite, not only at the Big Bang but also at the centers of black holes. These singularities represented the limits of general relativity's applicability. They were places where the theory broke down, where our understanding of spacetime's geometry ceased to be valid. Yet perhaps the most astonishing discovery came in 1998. Observations of distant Type Ia supernovae by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees revealed something that shattered astronomers' expectations. The supernovae appeared dimmer than they should have been if the universe's expansion were slowing due to gravity's attractive pull. Instead, the data suggested the universe's expansion was accelerating. Something was pushing the universe apart, overcoming gravity's pull, causing the expansion to speed up over time. This observation led to the revival of Einstein's cosmological constant, now reinterpreted as dark energy, a mysterious form of energy pervading all of space, exerting a repulsive pressure. Dark energy comprises approximately 70% of the universe's total mass energy content, yet its nature remains profoundly mysterious. Is it a fundamental property of space-time itself? Is it some quantum field effect? Is it a sign that general relativity itself is incomplete? In 2024 and 2025, data from the Dark Energy Spectroscopic Instrument, DSI, began revealing something even more mysterious. Preliminary analysis suggested that dark energy's strength may not be constant, as Einstein's simple cosmological constant would predict. Instead, dark energy's influence might be changing over time, growing weaker or stronger as the universe ages. If confirmed, this would suggest that spacetime's expansion is governed by something far more complex than a simple constant, something that evolves, that is dynamic, that changes. DSI researchers describe these findings as deeply intriguing. Will Percival, co-spokesperson for DSI, stated that the evidence for evolving dark energy is looking more and more like we may need to modify our standard model of cosmology to make these different datasets make sense together. The measurements had reached 2.82, 4.2 sigma, not yet the definitive 5 sigma, threshold that would constitute a discovery in physics, yet strong enough to suggest that a fundamental transformation in our understanding of space-time and cosmology may be imminent. There are places in the universe where space-time ceases to behave. These are not distant, irrelevant corners of reality. They are predictions of Einstein's equations themselves, consequences of general relativity's own mathematics. They are places where space-time breaks, where the familiar laws of physics collapse, where our understanding of reality shatters into paradox. These are singularities, and they reveal something profound. Einstein's beautiful equations, which have been tested and verified countless times, are incomplete. They work everywhere except at the places where they most desperately need to work, where matter is compressed to infinite density, where space-time is curved to infinite extremes. The first singularity was predicted by Carl Schwarzschild in 1916, just 1 year after Einstein published general relativity. Schwarzschild solved Einstein's field equations for the space-time surrounding a massive, spherical, non-rotating object. His solution described something extraordinary. If the object's mass were compressed within a certain radius, now called the Schwarzschild radius, space-time would curve so dramatically that nothing, not even light traveling at the ultimate cosmic speed, could escape. For a mass equivalent to Earth's, this radius would be about 9 millimeters. For the Sun's mass, approximately 3 kilometers. For a stellar mass black hole, perhaps 10 kilometers. If all this mass were compressed to such a density, it would create a black hole, a region of space-time from which escape was mathematically and physically impossible. The boundary of this region, the point of no return, is called the event horizon. It is not a physical surface. It is not made of matter. It is a boundary in space-time's geometry itself, a mathematical surface that marks the transition between regions of space-time from which escape is possible, and regions from which it is not. At the very center of a black hole lies something more extreme, the singularity. This is a point of infinite density, infinite curvature. According to general relativity, all the black hole's mass is compressed into this infinitesimal point. The curvature of space-time becomes infinite. The laws of physics as we know them cease to apply. For decades, many physicists believed singularities to be artifacts, mathematical curiosities that would vanish once a more complete theory of gravity, a theory incorporating quantum mechanics, was developed. Yet in 1970, Stephen Hawking and Roger Penrose proved something unsettling. Under very general conditions, general relativity predicts that singularities must exist. They are not avoidable. They are inevitable consequences of the theory's mathematics. Hawking and Penrose proved singularity theorems that shook the foundations of theoretical physics. Not only do singularities exist within black holes, but they also exist at the moment of the Big Bang. When one traces the universe's expansion backward in time using Einstein's equations, one encounters a singularity, a point in the infinite past where density and temperature become infinite, where space-time's geometry becomes infinitely curved, where time itself begins. The existence of these singularities represents a profound crisis. They are places where Einstein's equations give infinite, nonsensical answers. They are places where the very concepts of space and time break down. Hawking famously stated, "Singularities represent the breakdown of general relativity, and it is anticipated that a more comprehensive theory of gravity, quantum gravity, will eliminate these singularities. Yet the implications are unsettling. If singularities are fundamental features of our universe, existing at black holes' centers and at the moment of creation, then they are not mere mathematical curiosities. They are windows into physics at its deepest level, regions where the current framework of knowledge fails completely. Between 1965 and 1972, Hawking made another discovery that deepened the mystery. He proved that black holes are not entirely black. Due to quantum effects occurring near the event horizon, black holes should emit radiation. This radiation, now called Hawking radiation, means black holes are not stable forever. They slowly evaporate, radiating energy into space until they completely disappear. This discovery united quantum mechanics and general relativity in an unprecedented way, showing that the two pillars of 20th century physics were not as separate as previously believed. It also created a profound paradox. If a black hole evaporates completely, what happens to the information of all the matter and energy that fell into it? According to quantum mechanics, information cannot be destroyed. Yet according to black hole thermodynamics, information should be lost forever. This information paradox remains unresolved, a wound in theoretical physics suggesting that our understanding of both black holes and quantum mechanics is incomplete. Beyond singularities, space-time exhibits other extreme behaviors. In 2015, the LIGO Gravitational Wave Observatory detected something extraordinary: ripples in space-time itself. Two black holes, orbiting each other at a fraction of light speed in a system 1.3 billion light-years away, had finally spiraled into each other and merged. As they collided, space-time itself oscillated. These gravitational waves, ripples in the fabric of space-time, propagated outward in all directions at the speed of light. The detection of gravitational waves confirmed one of Einstein's most audacious predictions and revealed something profound. Space-time is not inert. It is not merely curved by matter and energy. It can oscillate, vibrate, ripple, carry energy. Space-time is an active participant in cosmic events, a dynamic entity rather than a static backdrop. Yet as space-time's properties have been explored more deeply, another mystery has emerged: false vacuum decay. Quantum field theory suggests that the vacuum, the lowest energy state of space-time, may not be the true lowest state. The universe may occupy a false vacuum, a metastable state of apparent stability that could spontaneously decay into a lower energy, true vacuum. If such a decay occurred, a bubble of true vacuum would expand outward at the speed of light, destroying everything in its path. The very laws of physics would change inside this bubble. Particles would have different masses, forces would behave differently, life as we know it would be impossible. The probability of false vacuum decay occurring in any given volume of space, in any given unit of time, is extraordinarily small. The danger is not imminent, yet the theoretical possibility haunts physicists like a cosmic sword of Damocles. A reminder that space-time itself may be unstable at its deepest level, that the universe we inhabit may be temporary, contingent, destined for transformation or destruction. These singularities and extreme phenomena, black holes, the Big Bang, gravitational waves, false vacuum decay, are not separate mysteries. They are all facets of a single, deeper mystery: the nature of space-time at its limits. They are places where Einstein's equations predict absurdity, where space-time's geometry breaks down, where our physics becomes incomplete. They are invitations to a deeper theory, a more profound understanding of reality's foundation. For over a century, physicists have stood at an impasse, facing two incommensurable truths. On one side stands general relativity, Einstein's theory of gravity, which describes space-time as a smooth, continuous, classical entity. Space-time in general relativity is like a rubber sheet. It can be curved, stretched, deformed, but it remains fundamentally continuous. The universe, in this framework, is a smooth, geometric manifold extending infinitely in all directions. On the other side stands quantum mechanics, the theory that governs the atomic and subatomic realms. Quantum mechanics reveals that reality is fundamentally probabilistic. Particles exist in superposition, existing in multiple states simultaneously until observed. Properties like position, momentum, and energy are quantized. They come in discrete units, cannot take on arbitrary values. The quantum realm is grainy, discontinuous, fundamentally different from the classical smoothness of Einstein's spacetime. These two pillars of 20th century physics are incompatible. More precisely, they are incompatible at the places where both matter and gravity are strong, at the centers of black holes, at the moment of the Big Bang, at scales approaching what is called the Planck scale. The Planck scale represents the boundary between the classical and quantum realms. The Planck length is approximately 1035 meters, inconceivably small, smaller than any directly observable length scale by many orders of magnitude. The Planck time is approximately 1044 seconds. At scales smaller than these, quantum gravity effects should dominate. The smooth classical spacetime of Einstein breaks down. Quantum effects become supreme. But what happens at the Planck scale? What is the structure of spacetime at such infinitesimal distances? No experimental apparatus humanity has built, or could practically build with known physics, could directly probe such scales. Yet theorists have developed approaches, speculative frameworks attempting to unify quantum mechanics and gravity. One such approach is loop quantum gravity, developed by physicists including Carlo Rovelli and Lee Smolin. Loop quantum gravity suggests a radical possibility. Spacetime is not continuous at the Planck scale. Instead, spacetime is quantized. It comes in discrete units, atoms of spacetime. The smooth, classical spacetime we experience at everyday scales is an emergent phenomenon, like the smooth surface of water emerging from the discrete collisions of water molecules. In loop quantum gravity, spacetime geometry is not a fundamental property of the universe. Rather, it is one aspect of a more fundamental quantum structure. Spin networks, mathematical structures representing quantum states of spacetime geometry, replace the classical notion of continuous spacetime. Space itself becomes discrete, pixelated, like a cosmic mosaic at the smallest scales. The implications are profound. If space is quantized, if there are discrete units of spatial extent smaller than which nothing can exist, then the very concept of empty space is altered. There is no infinitely small, infinitely divisible continuum of space. There are discrete quanta of space. Volume itself is quantized. An alternative approach comes from string theory, which proposes that the fundamental objects in nature are not point particles, but tiny vibrating strings. String theory naturally incorporates gravity, and it predicts quantum corrections to classical gravity's predictions. Yet string theory requires something that has always troubled physicists: extra dimensions. Beyond the 4 dimensions of spacetime, 3 of space and 1 of time, string theory proposes that 6, 7 or more additional dimensions exist, compactified at scales too small for direct observation. Recent data from DESI, mentioned in connection with evolving dark energy, has renewed interest in string theory. Certain string theory models predict quantum corrections to dark energy that align surprisingly well with DESI's tentative findings of evolving dark energy. Whether this represents genuine agreement between string theory and observation, or mere coincidental alignment of parameters, remains hotly debated. Yet perhaps the most radical idea to emerge from attempts to quantize gravity is the holographic principle. Proposed by Juan Maldacena in 1997, the holographic principle suggests something almost incomprehensible. The universe might be fundamentally lower dimensional than it appears. Imagine a 3-dimensional room with objects inside it. According to the holographic principle, all the information describing every object in that room, every property, every interaction, every possible event, could be completely encoded on the 2-dimensional surface of the room's walls. The 3-dimensional reality we perceive would be a projection of this lower dimensional information, like a hologram. Applied to the universe, the holographic principle suggests that all information describing the universe, all of spacetime, all of physics, could be encoded on a lower dimensional surface at the universe's boundary. The 3-dimensional universe we inhabit, with time as a 4th dimension, would be a hologram projected from a lower dimensional information structure at infinity. This is not mere speculation. Maldacena developed this idea through the ADS-CFT correspondence, a mathematical relationship between certain quantum field theories and gravitational theories. The correspondence has been extensively studied and has provided insights into the nature of black holes and quantum entanglement. Yet the full meaning of the holographic principle remains mysterious. In 2023, physicists began exploring whether the holographic principle might be testable in laboratory settings. Researcher Monica Schleyer-Smith and colleagues at Stanford University used ultra-cold atoms trapped in optical lattices to simulate quantum systems where space-time emerges from quantum entanglement. In these systems, spatial geometry is not fundamental. It emerges from the entanglement structure of the quantum state. If space-time emerges from entanglement, then the separation we perceive between distant points in space may be illusory. All points might be fundamentally connected through quantum entanglement. The classical notion of locality, the idea that distant objects cannot instantaneously influence each other, would be modified. Spacetime's apparent locality would be an illusion, created by the coarse graining of underlying quantum entanglement. Physicists are now developing experimental approaches to test directly whether spacetime is continuous or discrete, classical or quantum. These approaches, collectively termed the squeeze, involve precision measurements from multiple angles. Gravitational wave detectors like LIGO are being pushed to higher sensitivities, attempting to detect the grainy, discrete nature of spacetime at their limits. Simultaneously, experiments using ultra-cold atoms and interference patterns are approaching the question from the opposite direction, searching for evidence of quantum spacetime in laboratory conditions. Within the coming decade, these experiments may provide the first direct evidence for one or the other scenario, that spacetime is fundamentally discrete, quantized, perhaps even emergent from quantum entanglement, or they may reveal something entirely unexpected. A third possibility that neither loop quantum gravity, nor string theory, nor the holographic principle has yet conceived. Either way, the century-long impasse between quantum mechanics and general relativity may finally be approaching resolution. After a century of investigation, physicists have discovered that spacetime is far stranger than Einstein imagined. Yet perhaps the strangest possibility is also the most radical. Spacetime may not be fundamental at all. It may be emergent. In the traditional understanding stemming from general relativity, spacetime is fundamental. It is the foundational layer of reality. All other phenomena, particles, fields, forces, exist within spacetime or are propagated through spacetime. Spacetime is the stage, and everything else is the play. Yet recent theoretical developments suggest a different possibility. What if spacetime itself is not fundamental? What if it emerges from something deeper? What if space and time, which seem so basic and elementary, are actually derivative properties arising from more fundamental quantum structures? This idea is not new. Philosophers have long debated whether space and time are intrinsic properties of reality, or merely useful concepts for organizing our perception. Kant argued that space and time are forms of human intuition, structures through which we perceive reality rather than properties of reality itself. String theorists and quantum gravity researchers have extended this philosophical insight into a concrete scientific hypothesis. If spacetime is emergent, then from what does it emerge? One compelling possibility involves quantum entanglement. Quantum entanglement is the phenomenon where two or more quantum particles are connected in such a way that the measurement of one particle instantaneously influences the others, even if separated by vast distances. Einstein famously called this spooky action at a distance, troubled by its apparent violation of locality. Yet modern physics increasingly recognizes entanglement as fundamental. Some theorists have proposed that entanglement is not merely a quantum phenomenon occurring within spacetime. Entanglement might be the mechanism by which spacetime itself is constructed. Consider a thought experiment. Imagine a quantum system in an entangled state. This entangled state can be represented as a tensor network, a mathematical structure where each node represents a quantum subsystem, and each link represents entanglement between subsystems. Remarkably, the geometry of this tensor network resembles spacetime geometry. The distance between nodes in the tensor network corresponds to the causal distance in spacetime. How much quantum information can flow between them if this correspondence is not merely mathematical coincidence but reveals a deeper truth? Then spacetime might be constructed from entanglement. Points in spacetime that appear distant in classical geometry might be nearby in quantum entanglement space. The apparent locality of spacetime, the fact that distant objects cannot instantly influence each other, would emerge from the pattern of entanglement connections. This perspective offers a radical reconceptualization of what spacetime is. Rather than a fundamental container within which quantum events occur, spacetime would be a description of quantum correlations. The continuity of spacetime would emerge from the density of entanglement connections. The dimensionality of spacetime, why we experience 3 spatial dimensions and 1 temporal dimension, might be determined by the structure of quantum entanglement in the underlying theory. Another perspective suggests that spacetime is fundamentally informational. This approach builds on discoveries by Jacob Bekenstein and Stephen Hawking regarding black holes. Bekenstein discovered that black holes possess entropy proportional to the area of their event horizon, not their volume. This was shocking, because entropy is usually proportional to volume. For a black hole, entropy is encoded on its 2-dimensional surface, rather than in its 3-dimensional interior. Hawking interpreted this to mean that black holes are thermodynamic objects with a well-defined temperature. The more Hawking studied this, the more he realized that information and entropy in black hole physics are intimately connected to spacetime's geometric structure. Some theorists have proposed that this relationship is fundamental. Spacetime coordinates are not absolutely real quantities describing positions in an external container. Rather, they are emergent concepts describing relationships between information. In this informational view, the question, "Where is a particle?" does not have an absolute answer. The particle's location is defined relative to other particles and systems. Spacetime, the coordinate system we use to describe positions, emerges as a convenient description of information relationships. Different observers with different information about the system might describe it using different spacetime coordinates, yet the underlying information content would be the same. These perspectives converge on a single, unsettling conclusion. Spacetime is commonly understood as a fundamental, absolute stage for the universe's drama does not exist at the deepest level. Spacetime is derivative, emergent, a description of underlying quantum structures rather than a fundamental ingredient of reality. The return to prominence of dark energy provides another clue. The DESI collaboration's tentative finding that dark energy may be evolving over time, rather than constant as the cosmological constant would predict, suggests that spacetime's properties are dynamic at a fundamental level. What could cause dark energy's strength to change? One possibility involves quantum vacuum fluctuations. In quantum field theory, even the vacuum, the lowest energy state of spacetime, is seething with virtual particles constantly appearing and disappearing. These fluctuations contribute to the vacuum's energy density. In a quantized spacetime, where spacetime itself is granular at the Planck scale, vacuum fluctuations might have a character different from what we expect in flat spacetime. The density of these fluctuations, and thus the apparent strength of dark energy, might vary with the expansion rate or other properties of the cosmic evolution. Another possibility is more speculative. Dark energy could be a manifestation of conscious observation or quantum measurement effects on macroscopic scales. This is not to say that consciousness causes dark energy. Rather, if spacetime is fundamentally informational or emergent from quantum entanglement, then the process of information becoming actualized through observation might have effects on spacetime's properties. At the deepest level, there remains a profound mystery regarding time itself. In Einstein's equations and Minkowski's spacetime, time is merely another dimension, fundamentally no different from spatial dimensions. Yet our experience of time is radically different from space. We can move freely through space, but not through time. We experience temporal flow, an arrow of time pointing from past to future. We have memory of the past, but not the future. Yet the equations of physics, both Einstein's relativity and the quantum mechanics of Schrödinger, are fundamentally time-symmetric. If you reverse the direction of time, the equations still hold. So why does time appear to flow? Why is there an arrow of time? This question has troubled physicists and philosophers for generations. Entropy provides part of the answer. The second law of thermodynamics states that entropy, disorder, randomness increases over time. This gives time a direction, the direction of increasing entropy. Yet entropy is a statistical concept arising from the averaging of microscopic quantum states. At the quantum level, individual processes are reversible, time-symmetric. The arrow of time might be emergent from our macroscopic perspective on quantum systems. In this view, time does not truly flow. Rather, all moments, past, present, and future, are equally real in the four-dimensional space-time block. Our sense of temporal flow is an artifact of our limited knowledge and attention. But if space-time is emergent from quantum entanglement, then time might have an even more fundamental character. The temporal ordering of events, which event causes which other event, might emerge from the causal structure of quantum information. Time's arrow might reflect the direction of quantum decoherence, the irreversible process by which quantum superpositions become classical definite states. These speculations point toward a unified vision of reality far stranger than classical physics. In this vision, space and time are not fundamental. Consciousness and observation are not peripheral to physics, but potentially central. The universe is not a collection of objects located at particular points in space-time, interacting through forces. Rather, the universe is a vast network of quantum entanglement, and space-time, along with our experience of space, time, locality, and causality, emerges from the structure and evolution of this entanglement. Yet this vision remains speculative. The experiments that might confirm or refute it lie ahead. The mystery deepens because the deeper we look, the less certain we become about what we thought we knew. We have journeyed from Newton's absolute space and time, through Einstein's geometric revolution, into the quantum realm where space-time itself becomes uncertain. We have discovered that the universe is expanding, accelerating. That mysterious dark energy fills the cosmos. We have learned that space-time can be torn, twisted, converted into ripples of gravitational waves. We have glimpsed the possibility that space-time is not fundamental but emergent from quantum entanglement at scales too small for direct observation. What does this mean? What are the implications of these discoveries for our understanding of existence itself? At its deepest level, space-time research is not merely a scientific endeavor. It is a philosophical investigation into the nature of reality. It is an attempt to answer the oldest human questions. What is the universe? What is my place in it? What is the nature of time and existence? How did this all begin? The discoveries of modern physics suggest that reality is far more subtle and counterintuitive than our everyday experience suggests. The solidity of the material world, the inevitability of physical laws, the clear distinction between observer and observed. All of these apparent certainties have been undermined by 20th and 21st century science. In quantum mechanics, the act of observation affects reality. Before an observation is made, a quantum system exists in superposition, in multiple states simultaneously. Only upon observation does the superposition collapse into a definite state. This is not metaphorical. It is a core prediction of quantum theory, confirmed countless times in laboratory experiments. The universe, at its quantum foundation, is participatory. Observer and observed are not completely separate. If space-time is emergent from quantum entanglement, then this participatory nature of reality extends to the very fabric of existence. Space and time, which seems so objective, so independent of any observer, would be emergent from the quantum correlations between systems. In a universe with no observers, no quantum measurements being made, the concepts of space and time might have a different, even undefined meaning. This does not mean that consciousness creates the universe in a literal sense. It does not mean that the universe only exists when observed. Rather, it suggests that reality, at its deepest level, is not divided into an objective external world and a subjective internal observer. The distinction between subject and object, between mind and matter, might be less fundamental than our intuitive experience suggests. Consider the problem of false vacuum decay. The universe may be in an unstable state, one that could spontaneously transform into a lower energy state at any moment, destroying all physics as we know it. The fact that this has not yet happened, the fact that the universe has evolved to the complexity it has, may suggest that reality is more carefully balanced, more improbable than we imagined. Some physicists have invoked the anthropic principle. The universe is the way it is because if it were different, we would not be here to observe it. Yet this principle raises a profound question. Is it coincidence that the universe's fundamental parameters allow for complexity, for stars and planets, for life and consciousness? Or is there something deeper, something that selects for universes capable of generating observers? Multiverse theories suggest that perhaps countless universes exist, each with different fundamental constants and laws. We happen to inhabit one of the rare universes where conditions permit intelligent life. In this view, the apparent fine-tuning of physical constants is not surprising. It is inevitable that we find ourselves in one of the special cases. Yet these ideas remain speculative. The multiverse is not directly observable by definition. We cannot know whether universes exist beyond our own. What we can know is this. The universe revealed through physics is far stranger and more wondrous than it appears. Space-time is not a stage but a participant, not immutable but dynamic, not fundamental but perhaps emergent. Time is not absolute but relative, not flowing but possibly emergent from more fundamental quantum structures. Reality is participatory, observation-dependent, fundamentally quantum at its base. These discoveries should inspire not despair, but wonder. The fact that reality is so counterintuitive, so difficult to comprehend, so far from common sense, suggests that human consciousness has the capacity to comprehend something profound. In discovering the quantum nature of reality, in developing general relativity, in speculating about the holographic principle and quantum entanglement, humans have demonstrated an extraordinary capacity to transcend intuition and grasp the deep structure of existence. The mystery of space-time remains unsolved. Future discoveries may overturn what we believe today, just as our ancestors' beliefs have been superseded. Yet the pursuit of understanding, the effort to comprehend reality as deeply as possible, is itself meaningful. It reflects something essential in human nature, The desire to know, to understand, to place ourselves within a coherent picture of existence. Time is a mystery. Space is a mystery. Their origin and ultimate nature remain unknown. Yet in pursuing these mysteries, humanity pushes forward the frontier of knowledge. And perhaps in the process of understanding the universe, we come to understand something about ourselves, not as separate observers outside reality, but as conscious beings woven from the same quantum entanglement that constructs space-time itself. The universe is not finished revealing its secrets. Neither are we, and in that ongoing revelation lies perhaps the greatest mystery of all. Consciousness contemplating itself through the lens of physics, existence seeking to understand existence, the universe becoming aware of itself through the eyes of those who inhabit it.